OK， 好，那我们 start today's lecture，OK？ 看一下，大家有看到我的荧幕吗？没有。OK， 这样子呢，有了，好 ，OK， 好，那我们就开始今天的 lecture。Start today's lecture. Today we're going to talk about deadlock situation or deadlock in terms in general in the operating system. Now, so let's first take a look at the problem statement, problem of the deadlock. What is a deadlock in the operating system? Now, we have been talking about that already. A deadlock is a set of a block process that's holding the resource that waiting inquire another resource that's holding by another process in a set. Okay, it means waiting for one another. For example, if a system has a 2-disk drive, okay, if P1 and P2 hold one disk drive, and each needs a resource from the other disk drive, then that means P1's, let's say P1's holding a disk 1, P2 holding a disk 2. But P1 needs disk 2, which holding by P2. P2 needs disk 1, which holding by P1. So means P1 and P2 waiting for each other. Okay, so inquire that resource are held by another process. So it means P1 and P2 create what we call the deadlock problem. Okay, another example is a semaphore. Okay, which we have been giving. I have a semaphore A and B, which they are initialized to 1. Then I have a P0 and P1. They are holding this. They are trying to get a semaphore, which semaphores means they are holding, they are governing some shared resource, right? So let's say P0 call for wave function on A, semaphore A, and P1 call for wave function on semaphore B. Then next when they request for P0 waiting for call for B, and P1 call for A, they are, guess what? They are locking off each other. So P0 is holding A, waiting for B. Now P1 is holding B, waiting for A. So they are locking on each other. Okay, so that's a deadlock problem. Another problem you can think of as a bridge crossing example. If a traffic has only one direction, or the process going on for forwarding direction, or process going on continue, each section of the block can view as a resource or can hold as a critical section. The data can occur that it can be resolved, right, if both that entering that critical section, okay, all want to ask for that resource, the shared resource. If one can back up or preempt this resource and roll back, then you have no issue. Okay, so that means you might have a several card that or several process that needs to back up, okay, before the deadlock can occur. Okay, however, the can resolve. However, the starvation can still be possible if you continue to hold a specific resource. Okay. That means they are waiting forever for that resource. Even though they're backing up, they're still waiting for that resource. They continue to the backup, roll back. Okay, in that situation, one process might wait forever for that resource, means starvation. Okay, so now notice most operating system does not prevent or deal with the deadlock. Okay, they try to make the best out of it by using a critical section, but they're not preventing or they're not dealing with the deadlock situation. All right. However, let's take a look on the system model. Usually, we try to model a software system or a system or a program, okay, as a set of resource. Okay. You might have a resource 1, resource 2 to resource M. Okay, now that resource could be a CPU cycle, could be a memory space, could be some I/O device. All those we count as resource. Now each of those resource, right, has specific number of instant or number of copy of instant. Okay, so each resource R we have a W instant. Now each process Y tries to utilize this resource as follow. Okay, I try to request it, I try to use it, and I release this resource. So this is very similar to what? To the critical section, right? I lock on the request a lock, and I enter the critical section, and I exit the critical section by release them, right? So it's very similar. So now we look at the system model. How do we deal with this? How do we model this deadlock situation or deadlock characteristic? So now remember the system model. We have a resource, we have the process, each resource has instant. Okay, you need to request, use, and release. Okay. All right, so now let's take a look on the characteristic of the deadlock. Now the deadlock can occur in this four condition if it holds simultaneously, okay, at the same time. First is the mutually exclusion. If there's only one process at a time can use a specific resource, that might create a deadlock. Hold and wait is another characteristic. Hold and wait means a process holding one resource but waiting to inquire additional resource that's might held by another process. I hold a resource, I'm waiting for another resource, which that might create a deadlock. Okay. No preemption is another one, means a resource can be released only voluntarily by a process holding it after the resource being complete its task. Means that process might hold this resource and only release it when it's finished. Okay, mean no preemption, right? That might create a deadlock. Another one is most important is what we call a circular wait. Means what's that? That process resource has mutually exclusive. A process might hold one process, then waiting for another process, and that process cannot be preempted. And then at the end, if you have the circular wait, mean that you have exists a set of a process from P0 to Pn. That's a waiting process, such as that P0 is waiting for the resource held by P1. P1 is then waiting the resource that held by P2, so on and so forth. And Pn minus 1 is holding the resource by Pn. And in case if there's a Pn that's waiting for the resources held by P0, okay, or Pn before it, okay, then in that case, you will have what we call a circular wait. Okay? If there's a circular wait exists, this will have results of a deadlock. Okay, so now with that full condition that might hold simultaneous by a process in the system, we can use a resource allocation graph to somehow detect or somehow recognize there might be a deadlock, there might be a circle in the system. Now, the resource allocation graph is as follows. Okay, you will have a set of vertices V and set of edge E. Okay, they are all vertices. Okay, let's start again. I have a set of vertices and set of edge in the graph. Okay, the vertices is participating into two types. Okay, the first type is the process P1, P2 all the way to Pn. It's a set of a process that's in the system. You have another set of the vertices is R, which is R is a set of R1 to Rn, which consists all the resource type in the system. P and R, they are both vertices. Okay, from there on, you have two type of edge E. Okay, one is request edge, one is assignment edge. Now, request edge and assignment edge, they are all directed edge. Okay, means they have some direction. Okay, now the requesting edge or P of I means process I that's holding requests some resource. Assignment edge means a resource, some resource assigned to a process, some process. So in this case, the resource J assigned into process PI. Okay. So therefore, from there, the definition of that, we will have, we have two vertices, right? We have process I, Okay, I have I of the process, n of the process, 1 of the process pi. I have a resource, okay, Rj, okay, with 3 instance. At 3 instance, this is still a vertex, okay. That vertex has a 3 dark in the middle, means that I have 3 instance for that resource, okay. Then I have a p request some instant to resource Rj. Okay, the first is these 2 are the vertices, okay. The second thing is I have some process requested instant for Rj, okay. That is what we call a request edge, okay. Pi requesting some instant of what resource Rj. Then you have what we call the Pi is holding an instant of Rj. That's assignment edge. Then you have a direction edge from an instant of Rj that's assigned to process Pi. So you can see in this resource, you can have 3 instances that can assign to 3 different processes, or you can assign to some other process of two other processes. Okay, so therefore, for example, okay, if we have a resource allocation graph that could be like something like this, okay. Again, I have a set of a process P and set of resource and set of edge, okay. I have a process, what? P1 to P2, P3. I have 3 processes, right? And I have a resource, R1, R2, and R3. R1, R2, and R3, they all have a different number of instances, okay? For example, in the graph, look on the left, right side of the graph, you will have resource 1 have 1 instance, resource 2 have 2 instance, resource 3 have a 3 instant, okay, and resource 4 has a 3 instant, okay. Now you will have an edge right now, okay, as this instant of time, okay. I have a P1, okay, request for some resource of R1, okay. So P1, if by looking at this one, I have a P1 is holding an instant of R2, okay? So P1 is holding an instant of R2, so therefore I have a directional edge that's pointing from R2 of 1 instant to P1. And the P1 is requesting or waiting for an instant for R1, so I have a requesting edge to R1, okay? So in this case, the edge is this. I have a P1 requesting R1, a requesting edge. P2 is requesting R3, an instant of R3. And then what? And I have R1 assigned. R1 is assigned to P2. And R3, okay, sorry, R2, okay, is assigned to P1, okay. R2 is assigned to P2. So R2 have 2 instances. 1 is assigned to P1, 1 is assigned to P2. And I have R3, have 1 instant is assigned to P3. Okay, that's the current situation at the allocation graph, resource allocation graph. Okay. Now, so therefore we want to see if what's the example of resource allocation graph with a deadlock. Okay, so in this case, if let's say if P3 is now making a request, okay, to resource 2, okay, in that case you will create a circular weight. Okay, so I have one circle is P1 requesting R1. P1 is requesting to R1. R1 is holding or assigned to P2. P2 is requesting to R3. R3 is assigned to P3. Now P3 is making a request to R2. Okay, but R2 is held in by P1. That's one circle. Okay, but you see there's a 2 instance. So, but you see this so that the very first one has already 1 circle that goes around from P1 back to P1 to around and back to P1. But you have a second instant, but that second instant also create a circle which you have what? P2 is requesting R3. R3 is held in by P3. P3 is requesting for what? R2, and R2 has an instant held in by P2. Okay. Now, this is another circular way. Okay, so the last one actually is P2, not P1. Okay, so this is make a mistake. Let me correct it. Okay. So this is actually P2. Okay. All right. Okay. So you see, in this example, I have a 2 circle. Okay, and that circle, they all comes back to P3, which P3 requesting that requesting edge to R2, which cause us has a deadlock. Okay, so that deadlock cannot be prevented because I have both instant on R2. They are assigned one for P1, one for P2. That actually they all eventually that wants to request a resource R3, which R3 is being held in by P3, which create what we call a circular weight. Okay, so that cannot prevent a deadlock because now we have a circle in the resource allocation graph. However, you can that circle can not always guarantee that has a deadlock. Okay, in this example, if I have another resource allocation graph, okay, that resource allocation graph will have a P1 requesting R1, R1 is requesting what? P3. Sorry, R1 is held in instant by P3. P3 is requesting R2, but R2 is what? Holding by P1. So that's one circle. Okay, that's one circle in the resource allocation graph. However, it does not has a deadlock because what? Because for example, P4 might release an instant of R2, right? Then if that release instant of R2, then guess what? P3 can gain the access for R2, which release that circle. Okay, so in that case, or in the case of P2 can release instant for R1, and R1 can be assigned by P1, which breaks the circle, right? So in that case, this is the resource allocation graph with a circle, but there will have no deadlock. Okay. All right. So therefore, which gives us a basic fact. If a graph contains no circles, means we definitely no deadlock. However, if the graph contains a circle, if only one instant per resource type, then they definitely have deadlock. Okay. If there are several instances per resource type, then you possibly have deadlock. You need to trace on every single instance to make sure they have a deadlock situation. So it's only possible to have deadlock if you have several instances per resource type. Okay. All right. Any questions so far? 有没有任何问题 ？OK。好，有问题请就是 turn on your microphone，OK？ 大家听的还蛮清楚的嘛 ，so far, right? All right. Okay. So next thing we want to talk about how do we handle the deadlock situation, and later we're going to talk about deadlock prevention, deadlock avoidance, okay, and how to detect and recovery. So now let's first talk about how do we handle the deadlock. Okay, well, the very first thing, of course, we want to ensure, or definitely we can ensure a system will never enter the deadlock situation. Okay, but that kind of costs you. Okay, means you need to have certain measurement before every single request. So to ensure the system will never enter the deadlock. Okay, the second method is you allow the system to enter the deadlock, but then you try to recover the deadlock. Okay. All right. So you allow the enter, then you do the recovery. Okay. The third one actually is the most operating systems I should do. Is to actually ignore the problem, pretend that deadlock never happened in the system. Okay. This is actually used by most operating systems, including Unix. Okay. So it means they kind of avoid the deadlock. Okay. So Therefore, in some time in your system that you might have a process that waiting for a long time with no response. What did you do? You probably just closing that application and restart again, right? Closing the application is kind of like, you try to break the loop in the resource allocation graph, and you restart the program, right? So that's a lot of time most operating systems try to do. Okay, all right. So the method to handle deadline is first you prevent it. The second one is you let it handle a deadline, you detect them, and you try to recover it. Okay, so to deal with the deadline prevention, the very first one is you maintain, okay, or you restrain the way requests can be made. Okay, you restrict such that it's mutually exclusion. Means that it's not required for shared data resource. You must hold for non-shareable resource. Okay, that mutually excludes. But the mutual exclusion, before we've been talking about, it's quite costly, right? Especially for parallel processing or multi-core system. The second one is hold and wait, right? The hold and wait means you must guarantee in some whenever there's a process requests a resource, it does not hold another resource. Okay, means that require process to request to allocate all its resource before it actually being executed. Allow the process to make a request only when the process has none of them. Means if you want to let your process to execute, you need to let it hold all the resource that it needed before you do the execution. Okay, but again, hold and wait, if you try to do it this way, it has a low resource utilization. Okay, means you let the process you held every single resource that's needed before you even let it execute it. So it might wait at the waiting state for a really long time before you can grant it every single resource. Okay, so therefore it has a very low system utilization. It has a starvation issue. The third one is just say, how about do no preemption? Means if a process holding some resource request and another resource that cannot be immediately located, then all the resource needs to be released. If I try to hold all the resource, okay, if I try to request another resource but that's not available, then I release every single resource. Okay, then I need to preempt the resource and add itself resource, add the list of the resource to which the process is waiting for. Okay, so the process will only restart it when you can grant all the resource and the new resource that request. Okay, but that still has a problem, right? That still have, you're gonna wait for a long time. No preemption issue. Solution. Okay, the third one is the circular wait. Okay, you have to impose some order of all the resource type and request each process requesting resource in some incremented order. Okay, so you try to guarantee that process 1 will start before process 2, will start before process 3, will start before process 4, not process start, finish. Process 0 finish before process 1, finish before process 2, so on and so forth. Okay, you increase the you impose the order. Okay, that requests each of those resources, but that kind of does not make sense as well to do the process prevention. Okay, so the solution on prevention is a bit trade-off between the deadlock guarantee prevention to the system utilization. Okay, all right, so there's a prevention is a bit hard. Okay, how about we see we can do prevent avoidance? Okay, if we cannot prevent them, can we avoid it? Okay, can we avoid this deadlock? Okay, so now let's take a look at deadlock avoidance. Now the deadlock avoidance is to require that system should have some information, additional prior information. Okay, the simplest or most useful model is to request that each process to declare, okay, maximum number of resource for each of type that it might need in the future. So it means the declaration, kind of like your program, you declare certain resource at the beginning of your program that you want to use. Okay, so you want to declare the maximum number of resource of each type that you might use. Okay, And the deadlock avoidance algorithm, okay, can dynamically examine the resource allocation state to guarantee or to ensure they will never have a circular way, okay, to avoid to enter the deadlock, okay. The resource allocation state is defined by the number of available and allocated resource and the maximum demand of each process, or maximum demand of the resource that each process needed, okay. Now, so if you assume you have that, when a process making a request for additional or available resource, now the system must decide if the immediately allocation leaves the system in a safe state. If a process requests additional resource, I need to guarantee that resource, if I assign it to a specific process, can still leave the system in a safe state. Okay. Now, if there exists a sequence such as that, P1 to Pn of all the processes in the state, such as that, systems in a safe state, if I have a sequence of a P1 to Pn, right, that in the process, all the processes in the system, if the system's in a safe state, such as that sequence for each Pi, like we see in the sequence, the resource of Pi can still grant the request that can satisfy by the first, it's currently available resource, means that resource currently available in the system. And, or the second, the resource held in by Pj, such as that Pj is less than Pi, okay? Remember, I existing a sequence of P1 to Pm, okay? If a Pi can grant this resource, if the resource currently available or the resource held in by Pj, mean the Pj is less than Pi, so the Pj is execute or finished before Pi. In that case, that resource might be released by Pj. So if that's the case, then the system should be in the safe state. Okay. So that is what it means. Okay. So if the Pi resource needed but not immediately available by Pi, okay, then the Pi can wait until all the Pj finish. Okay. Remember, Pj is all the execution process should be finished before Pi. Okay. So when Pj finish, right, then Pi can obtain the needed resource, execute, return the allocation resource, and terminate. Then the Pi plus 1 can obtain the need for the resource from Pi. Okay, so on and so forth. So Pi finish, return the resource, Pi plus 1 can obtain the resource from Pi, or Pi minus 1, so on and so forth. Okay, so then once Pi plus 1 finish, Pi plus 2, okay, can get the resource on Pi plus 1, so on and so forth. Okay, so in that case, that system should be in what we call a safe state. Okay, all right, 有没有任何问题? Any questions? So the definition of this is pretty simple. Okay, if the Pi wants to request some resource, you need to make sure if the current resource is available, that'll be okay. Or if the current resource is not available, I have to guarantee that resource I want to request will be finished before process I. Okay, so means when they finish, they can return the resource and process I can gain that resource and continue to execute and finish process I and let Pi plus 1 continue on. Okay, all right. So therefore, there's a basic fact. Okay, the fact is this: a system in a safe state if there's no deadlock. Okay, so the safe state is very clear. The system in a safe state if there's no deadlock. The systems in an unsafe state. The systems in unsafe state. Okay, then there's a possibility of deadlock. Okay, only the possibility in the unsafe state. So previously we are talking about safe state, right? All right, the avoidance algorithm that we're going to talk about in the next is to ensure the system will never enter the unsafe state. Okay, so the avoiding algorithm to guarantee the system always stay in the safe state. Okay. All right. So now, it's kind of like queue. That's correct. Kind of like, but that queue order. Okay, so means I have you might have a set of process that comes in the system. Okay, as a queue. Okay, but you can rearrange that queue. Okay, means process 1, 2, and 3. Okay, you might rearrange them such as that each of those process can try to get the request will be finished before that. Okay, so means although it's similar as a queue, you need to rearrange the queue such in that order of the queue, you can finish one by one without a circular way. Okay, which create a deadlock. Okay, all right. So it does very feel like a queue, but you can rearrange the queue, the order inside the queue. Okay, all right. 好，有没有任何 any comments or suggestion 问题 ？Okay， 好 ，if not we continue on. Okay, now let's take a look on avoidance algorithm. So we try to avoid to enter the unsafe state, right? So we try to make sure everything is in a safe state. So the very first thing, it's a single instant of the resource type, means that every single resource has only one instant. In that case, we just simply use resource allocation graph. Okay, then the second one is if I have a multiple instant of the resource type, then in that case, we need to use what we call a banker's algorithm. Okay, the banker's algorithm again to guarantee that each of instant of the request can be granted to make sure the system is still in the safe state. Okay, so let's first take a look on the single instant. Okay, the single instant simply use what we call the resource allocation graph scheme. Okay, now the resource allocation graph scheme is this. Okay, instead I grant them. Okay, I add additional what we call the claim edge. The claim edge means that process P of I try to claim some resource J that's indicating process P of I, not P of J. P of I might request a resource RJ, which representing by dash. Let me try to correct that. God, I'm making so much mistake in the slide. Okay, means process I, okay, try to may request a resource to resource J. Okay, all right, let's request that. I will update the slide after we finish the lecture. Okay, so that's the claim edge. The claim edge can convert to the actual request edge when a process requests a resource. Okay, the requesting edge converted to the assignment edge when the resource actually allocated to the process. Okay, so the request edge and assignment edge is the same as what we talked about the resource allocation graph before. Okay, so when a resource is released by a process, assigned edge can be converted to the claim edge. Okay, the resource must be claimed prior in the system. Okay, so what it means is this. Okay, let's give an example to be quite clear. Okay, suppose we have a resource 1 and resource 2. Okay, I have a process 1 and process 2. Okay, so each of those resources has only one single instant. Okay, so there's no dark in the middle. Okay, just one instant. Okay, now we have what? We have a 2 dash line, right? P1 dash to P2, the dash line to P2, R2, sorry. P2 have a dash line to R2. Okay, that's clear. Now, this 2 is what we call the claim edge. Means P1 might request a resource to R2. Okay, P2 also may request a resource to R2. Now, these two are all going to request to R2. Now, the system's decision to decide which one to assign them to. Okay. Then we have the previous one, a requesting edge, which is P2 requests, actually making the request, waiting for resource R1. Okay, that's actually the requesting edge, means they're actually making a request and waiting over there. Okay, And the next one is assignment edge, means actually system currently already assigned resource 1 to allocate it to P1, okay? So now, if once we have this resource allocation graph and the claim edge, then we know what to do with the assignment, right? So in this case, it might be an unsafe state in the resource allocation graph such that if the system convert the claim edge to assignment edge, the resource of R2 now is allocated actually to P2, okay? If I assign, okay, the R2 or to P2, then in this case, what will we have? We will have now a circular wave. That circle indicating that a system is in an unsafe state. Now I have a circle way in here. Okay, I have what? I have R2 assigned to P2. P2 requests R1. R1 assigned to P1, and P1 might request in the future to R2. Okay, which this results a circular wave. Okay. So therefore, in a resource allocation class, suppose I have a process I requesting a resource Rj. Okay, the request can be granted if and only if the converting of that requesting edge to assignment edge does not result a formation of circle in the resource allocation graph. Otherwise, this request should be rejected, right? Okay, so in the resource allocation graph, if that conversion of the claim edge or assignment edge does not, right, form a circle in the resource allocation graph, okay, then you can assign that. Otherwise, it will result the system in an unsafe state, okay? So that's a single instance of the resource type. 有没有任何问题？好，没有问题的话，我们来看 the next one. We take a look on the second one. It's what we call the multiple instance of the resource type, which using what we call a banker's algorithm. Now, the banker's algorithm is a little bit complicated compared to the single instance algorithm, but once you get your heads off the multiple instance as a set of resource, then it becomes easier. So now let's first take a look. Okay, a banker's algorithm is for a multiple instance type of situation. Each process must priorly claim the maximum use of the resource. So each resource must tell the system, say, hey, in this process, I might use set number of requests resource. Okay, the maximum of it. Then the next thing, when the process is making a request to a resource, it might have to wait. Okay, let the banker algorithm detect. If the process get all the resource, it must return them in some finite number of amount of time. Means I requested, I will return them eventually. Okay, that's our assumption. Okay. So now we have with that assumption, we can take a look of prior knowledge or prior assume that the system will have, the information will have. Next thing, what we have is what we call the data structure for the banker's algorithm. Okay, now let's take a look on the data structure for the banker's algorithm. There n be number of a process, m be number of resource type. Okay, so I have an n process, m resource type. Okay. Next, what I have is available. Okay, available is a vector with a length of m. Okay, available j. Okay, let's say available of item j. Okay, let's just assume available j. Let's talk about available j for now. Available of j equals to k means there's a k instance of the resource type rj available. Okay. So it means available j means I have a resource type rj, okay, with k instance that's available. Okay, so available again, available is a vector. Okay, all right. The second one is the max. Okay, max is n by m matrix, okay? N by m matrix such that if I have a max ij, okay, max ij equals to k means a process I, my request at most, the maximum at most k instant on the resource j, okay? So max ij, process I, resource j equals k means process I, pi requests j's resource rj at most k instant, okay? All right. Then you have an allocation matrix. Allocation matrix is again is n by m matrix. The concept is the same thing. Allocated ij equals to k. Then it means p process I is currently allocate k instant of resource j, rj. Okay, so allocation ij equals to k means process I requests currently allocated j process of kth instant. Okay, so allocation ij equals to k. Okay, the next is the needed matrix. A needed matrix again is n by m matrix, which that a needed ij equals to k means a process I needed k more instant. I needed k more, okay, instant of resource rj to complete its task. Okay, so needed ij means process I for going to needed resource j at most k instant. Okay, k more instant. Okay, any questions so far? 有没有任何问题 ？Okay, so therefore, from there on, you can see the needed matrix, the needed ij, well, actually to get it from a maximum ij minus allocation of ij, right? A maximum I request a certain amount of resource, right? At most maximum of that, and minus how many I have been allocated. I mean, in the future, I need this amount more, right? I have a maximum minus has been allocated means I need a certain amount in the future. Okay. All right. How? If no question, let's look on a notation before we even jump ahead on the algorithm first. Okay. So let's look on the notation of comparison of vectors. Okay. Let's assume if we have x and y be a vector length of n. Okay. X is less or equal to y if and only if less or equal to y if and only if x of I x of all the item in the vector x is less than all the item in y, that's I. Okay, x of I less or equal to y of I for all the item of I, which I equal 1 to n. Okay, for example, if x, the vector x equals 1, 7, 3, 2, and y's vector equals 0, 3, 2, 1, then in this case, y is less or equal to x. Y is less or equal to x. Means what? 0 is less than 1, right? 0 is less than 1. 3 is less than 7. 2 is less than 3. And 1 is less than 2. So if all the item of y, okay, is less than all the item in j, in that case, y is less than equal to x. Okay. Now, if y is less than x means if and only if x is less, y is less than x, what less than equal to x, and y is not equal to x on any of those items in their vectors. Okay, all right. So now, each row in the matrix of allocation and need can be looked as a vector. Okay, now we refer each row of matrix, okay, is as allocate allocation I and needed I. Allocation I and needed I is every single line for all the resource for process I. Okay, and needed I means process I needed specific set of resource. Okay, so we look them each row, look them as a vector. Okay, we have a allocation and needed a matrix, and we look on each row as a vector. Okay, so now allocation I, again, that's why I say is equals to resource O allocated to process I. Needed I means all the resource needed by the process I to complete the task. Okay, so I is task. So I is the process. Okay. Any questions so far? 所以这些 notation so far right now still okay, right? So we have the notation because the notation is quite important. If it wasn't not clear, refers to this page. Okay. So with that saying, we're gonna take a look on the banker's algorithm for the safety algorithm. Okay. Now we have the safety algorithm. Let work and finish be vector. Work and finish still a vector. Okay. Lengths of m and n. Okay, respectively. Okay. Initializing work equals available. Okay. Finish of I equals to 4 for I. Okay. From 0 to n minus 1. So I have an n of them. Okay. They are all the process that finished. Okay. So factor of I to keep the track. Okay. If they are finished. Okay. So factor of I is recording on every single process. Are they finished or not? True or false. Okay. That's it. Okay. Now let's take a look on this one. I will try on the safety algorithm. We'll try to find an I, a process I, okay, such that both finish of I equals to 4, means they are not finished, and need of I is less or equal to work. Work right now it's equals available so far right now. Okay, so if no such thing exists, then you go to step 4. Okay, if this two no such thing exists, if then you go to step 4. If finish of I at O equals to true for all the I, means everything is finished. Okay, then in that case the system's in a safe state. Okay, if not, okay, if I find that any of the cases f of finish of I equals to 4, need of I less or equal to work, then I go to step 3. Okay, step 3 tells you that work equals to work plus allocation of I. I allocate what resource or to process I, then that equals to work plus the allocation. Okay, then finish I equals to 2, means I is finished. I'm going to next. Okay, then I go back to next step. Okay, you increment the I, then you go to the next I to try to find out any of those I equals to 4. Then I continue on. Okay, until I continue looping 2, 3, 2, 3 until the step 2 go to step 4, and that means I finish every single process, all the process in the safe state. Okay. All right. Okay. So sorry, it's resource available. I kind of skip ahead. Okay, of what I said. Okay. So now just go back to reverse that. Work equals to available means that all the resources are available. Finish of I means for each of process I try to finish. Initially set everything equals to 4. Okay. The need of I less or equal to work means the resource available resource needed by process I it's available. Okay. Again, need of I is equal to resource that needed by process I to complete the task. Okay. Then that should be less than equals to work. Okay, work right now set it into available at the initialization. Okay, all right, and work equals the work plus allocated means now I set the resource allocation to P of I and I add it to work. Okay, means the resource allocation I mean the resource allocated to process I. Now means the process I able to finish work which is available resource and then allocate a resource. Okay, so that's the safety algorithm. Okay, From there on, we will have request of I, okay? Once you have that, the request of I equals the resource vector for process I. If that resource of I, okay, of J equals to K, means the process I wants to have what? K instant, okay, K instant for resource J, okay? So means a process I wants to K instance of resource J. In that case, if a request of I means resource of I means every single item of the resource, okay, that I'm gonna request by process I is less than equal to needed I, a needed resource of all the resource for process I. If that's less than needed I, go to step 2. Okay, otherwise writing the error condition means whatever I'm going to request is bigger than whatever I needed in the beginning. Means since the process exists, it's a maximum claim in the initializing when I want to request my maximum of the resource, then they're writing an error. Okay, if that's not true, means I'm going to a step 2. In a step 2, the request of I, okay, on every single resource of process I is less or equal to available, right? If it's currently available, then I can able to go to step 3, okay? Otherwise, P of I, if that's not true, P of I must wait since the resource is not available. I mean, P of I must wait means I'm going to go to P of I plus 1, for example, right? But if it's true, if resource of I, request of I is less or equal to available, then I only pretend, okay, I have not actually allocated. I pretend this allocation of requests of the resource to P of I by modifying the following step, okay? Available equals to available minus the request of I, okay? Because I'm pretending to allocate this resource, so means available now need to go to minus the request of I, process I. The allocation equals the allocation of I plus request of I, means allocation I allocate certain resource. Now, that allocation resource need to add whatever that process I going to request, okay? So that's the total allocation for that process of I, okay? Need of I equals to need of I minus the request of I, means I needed this much of resource in the future, but I made that request, so I need less of the request by minus that request of I, okay? So after I did this, okay, if it's still in a safe state, and on the previous solution, if that's still in a safe state, that resource can be allocated to P of I. If it's not on the safe state on the previous side, then P of I must wait, and all the resource allocation will be restored. All the pretended allocation will back to original, okay? Then I'm gonna try another process, P of I plus 1, for example, to see if I can find a certain order, okay? I can guarantee grant this request. Okay, so that's a banker's algorithm, okay? Any question? Okay, if we take a look on the example, it should be very clear. The explanation of the banker's algorithm is a little complicated, but actually when you execute the algorithm itself, it should be very simple, okay? So let's take a look on the example, okay? So we take a look on the example. If I have a 5 process, P0 to P4, okay, P0 to P4, I have a 3 resource, type A, B, and C. Type A has a 10 instant, type B has a 5 instant, type C has a 7 instant, okay? So the maximum instant for A is 10, B is 5, C is 7, okay? Now, at a snapshot, at currently assignment of the allocation so far right now is this. I have a P0 allocate 1 instant from resource B. P1, I actually currently allocate 2 instant of resource A, so on and so forth. And you have a maximum, okay? The maximum I'm gonna request for each of those processes is the maximum matrix. P0 has a 7, 5, 3, means I'm maximally going to request 7 instance for A, 5 instance for B, 3 instance for C, no more than that, okay? And the same thing with the P1, 3, 2, 2, 3 instance for A, 2 instance for B, 2 instance for C, okay? All right, so from at the instant of certain time, T0, for example, then we have this. The maximum equals the process time I request, which is for J, which I said it. So at a certain time, okay, the allocation right now, it's a 7, 2, 5, means the total right now in the system, I have a 7 instance that's being requested by 7 instance of A is requested by P1, P2, and P3. P1 requests 2 instance of A, P2, 3 instance of A, P3, 2 instance of A. Okay, so right now I have a total 7 instance already assigned, okay, out of the 10 instance. Resource B, I have 2 instance. Resource C, I have 5 instance currently assigned to, allocated to one of those processes. A few of those processes. So in that case, okay, because I already have a set amount of instance for each one of them. So for A resource, I have a 10 instance maximally. So the 10 instance, 7 instance already been assigned or allocated to process. So left with 3 instance. So that 3 instance is available. So A now available 3 instance. Okay, allow other people to request. B has a 3 instance, okay, because 2 instances already be assigned, allocated to P0 and P3, okay, which left off with 3 instance for B, and 2 instance for C, okay, because I have 5 instances already allocated to P2, P3, and P4. Okay, so available vector now is 3, 3, 2. Okay, all right. Now, what's that saying? The content of needed matrix now is defined as this. Okay, needed matrix is what? Needed ij equals maximum of ij minus allocate of ij. Okay, so in that case, I can calculate the needed matrix based on my allocation matrix. Maximum matrix minus the allocation matrix, okay, which give us the needed matrix as this, okay? So in that case, the system could be in a safe state, okay? If I can use the Banker's algorithm and gain this sequence, I can gain P1, P3, P4, P2, and P0. Means P1 finish, right? Because currently what? Currently before the available matrix is what? The available matrix on previous one is what? 3, 3, 2, right? Available, not matrix. Available vector is 3, 3, 2. Okay. Sorry. Available matrix 3, 3, 2. We finish this one. We take a little break. Okay. All right. Sorry. Available matrix 333, 332, okay? So it means I can finish P1, which P1 is right now is what? 1, 1, 2, right? Once P1 is finished and can release all the P1's allocated resource, then P3 can continue on as a 0, 1, 1, right? A needed additional one. Then P3 finish, return all the resource, P4 can go on. P4 finish, P2 can go on. P2 finish, P3 can go on. So this satisfies what we call a safety algorithm, safety criteria. In that case, this sequence can be granted, okay, to execute in a safe state, okay? Now, how about this? If P1, let's say in additional, at the certain state, at that current instant, if the P1 make the request of 102, in that case, if P1 make a request of 102, can it be a safe state? Okay, so we check if P1's request is less or equal to available. Okay, that is that request 102 available right now is the 332, right? So 332 is actually greater than 102, so that's true. So that means I can then grant it for P1's request. Okay, that request can be granted. Okay, and the P1, once P1 granted this request, P1's allocation is from 022 plus the request 102, which equals 302. Then right now the allocation vector for P1, okay, or allocation 1 will now equals 302. Okay, now when you execute that safety algorithm, okay, that sequence 1, 3, 4, 2, P0, okay, so P1, P3, P4, P2, P0 is still in the safety requirement. Okay, so in that case, this request, P1's request, can be granted. Okay, because after I grant it, it's still in satisfy the safety algorithm requirement. So how about, can I grant a request of 330 for P4? And the second question is, can I grant a request for 020 by P0? So now let's take a look. Okay, for P4 to grant a request 330, let's take a look. Okay, P4 currently actually allocated 002. Okay, 002 plus 330 actually right now becomes 332. Okay, right? So 002 plus 330 equals 332. Okay, so can 330 be granted? Okay, I need to check. Okay, the request of a P4. Okay, that request after I made that request of P4, process 4, is less or equal to available. Okay, that is 330 less than actually currently available 230? Actually the answer is no. Okay, because after I grant a P1's request, I cannot grant a P4 330 request because I do not have available resource to do so. So P4 will not follow by P1's request on the previous one. Okay, so that equals to 4. Because the resource actually is not available, so that P4 will get bumped out and let it execute later on of the execution. So how about P0 request 020? Okay, now let's take a look. Can the P0 request 020? Okay, we first check the request of 0. Is that less or equal to available? Okay, the thing is 020 at a P0 currently allocated 010, which equals 030, which is actually less than 230. So now it's 2. You can allocate it because now the resource available. Now, so we said P0 equals 010 plus 020 equals 3030. Okay. Now the allocation for resource of P0 is 030. Okay. Now it's still less than available. Now I update the available becomes 210. Okay, because 230 minus 020 equals 212. Okay. Now let's take a look. We said that work. We said the work equals is equals to 230, right? Work equals available. Okay. Works plus works equals to work plus allocation of I, which is 230 plus I allocated to 020, which now work is 250. Okay. Now we say the available minus that request. Available now I minus this request. Okay, is 230 minus 020. Now the available we said is 210, right? Okay. Now we say the allocation request. Allocation I equals allocation I plus the request of I. So the allocation 0 equals 010 plus 020 equals 030. Now this pretended allocation equals 0230. Now neither I equals neither I minus request. Now there neither I now equals neither sorry again, neither I equals 743 minus 020. 743 minus 023. So my 020 equals 723. Okay. Now we have work of I should be less or equal to, so neither I should be less or equal to work. Okay. But neither zero right now 723 actually is not less or equal to work, which work right now is 250. So in this case, means if I grant a process P0 on this request of 020, in the future, I may not able to let P0 finish. So in that case, I will also reject P0's request. Okay, because in the future that will happen. So in that case, all this pretended assignment will roll back to original before I assign it. Work plus works allocate, available equals available minus request, allocate I equals allocate I plus request I do all the rollback. Neither I equals neither I minus request. All this I will roll back to the original and try another assignment. Okay, so that is Banker's algorithm. They pretend to assign to make sure the order of the execution of that process 0 and I can able to make the request. Okay, so answer that previous comment. So it does look like a queue. You rearrange the order of the item inside the queue to make sure it can pass the Banker's algorithm. Okay, the safety algorithm. Okay, any questions so far? 有没有任何问题 ？OK， 没有问题吗？没有问题，我看一下哈，我们应该只有几张 slide， 我们要不要 continue 啊？好，我们只有10张 slide， so 我们要休息一下，还是我们继续下去？喂，同学有没有什么建议？我们继续下去吗？休息，好，好，我们休息一下。如果你需要的话，我可以解释给你听。你可以打开你的麦克风 ，OK。好，那我们就休息一下 ，OK。然后我看看4:40，我们想4:40啊，我们4:50我们再回来，只剩下10张 slide， 所以我们4:50就回来，我们 take a 10-minute break， 好吧 ？All right, OK。好，那我先停止录影，然后你有问题可以问 ，OK。好，算了，其实我不用停止录影。好，你有问题，可能别的同学有问题。好，来，有什么问题？为什么刚刚是 P1 P3 ？OK， 刚刚那个顺序就是它可以完成，你说这个顺序嘛，对不对？这个对，这个顺序其实就是当你跑完这个 Banker's algorithm 的时候，当你跑完这个 safety algorithm 的时候，因为 safety algorithm 说什么 ？safety algorithm 要一直去找它 ，OK？Safety algorithm 一直去找它 ，if finish of I equals to 4的话，然后 need of I 就是小于 less than word 的话，我就 continue on。如果没有的话，我就去这边，我就去 step 4。如果有的话，我就去下一个。我把 work allocation I 这样把它试着做到这件事情。如果可以的话 ，finish of I 会等于 true， 然后我再回到 step 2。如果不行的话，我要再换下一个。OK， 所以表示当你跑完这个 safety algorithm 的时候，其实它的 order 就会变成 P1 finish， 然后 return 所有的 resource， 然后 P3 才能 finish return 的 resource P4、P2、P0。对，所以这是一个 sequence， 可以让整个 system in the safety state。 OK， 所以就像是刚刚有一个同学讲说很像 Q， 但是它又不是 in the Q order， 因为这个 safety algorithm 要 rearrange 这个 order， 让它的 execution 可以 in a safe state， 所以这个 order 就会是 system want to execute 让这些 process finish the order。OK， 它也许不是currently execution 的 order， 但是它必须是 P1 一定要 finish before P3，P3 一定要 finish before P4，P4 一定要 finish before P2，P2 一定要 finish before P0。Okay, in this order, this sequence will satisfy the safety algorithm. Okay. OK， 好，你可以回去试一下这个翠星这个 algorithm， 你就可以 figure out 就是 P3、P4，不是 P1、P3、P4、P2、P0 will satisfy the safety algorithm。Once you have 这个 algorithm 的话，你就知道，哎，原来这个就会 guarantee the whole system still stay in the safe state。OK， 就像我们刚刚讲的，systems in a safe state， 哎，systems in a safe state is definitely will have no deadlock， 但是是 in the unsafe state not always guarantee 会是 deadlock。OK， 所以这个 safety algorithm 是试着让 all the process stay in the safe state。OK， 好 ，OK， 还有没有任何问题？好，没有问题的话，I'll stick around. OK， you guys can come back at 4:30， 然后4:30sorry 不是4:30， 4:50， 4:50，然后回来的话，we continue on for the last topic on the deadlock. OK。好，一样，如果你有问题，你就 turn on 你的麦克风 ，OK？I'll stick around。 OK，好，我们再回来下半堂课。OK，那一样do a quick sign in next of the class。我觉得你们应该要写一个爬虫，还会自动侦测老师打完字之后，你们就 automatic type in All right, so let's start the next half of the class. Okay. 好，那我们next one we're gonna to take a look. We have the avoidance. The next thing is to deadlock detection and how do we do a recovery. Okay, this actually is not as hard as you think. Okay, all right. So let's take a look on the deadlock detection. Okay, now the deadlock detection is this. Okay, usually in a lot of systems you allow the system to enter the deadlock. Okay, once you enter the deadlock, you run the detection algorithm. So once in a while, you run that detection algorithm to detect if the system in a deadlock state. If it's deadlock state, of course you try to recover it in such a deadlock state. Okay. So in a single instance type of each resource type, and remember we say we maintain a waveform graph or a system allocation graph, right? A resource allocation graph. Sorry, resource allocation graph. Now we try to convert the resource allocation graph back into a waveform graph. I'm going to explain what the waveform graph is. The waveform graph is a simplified resource allocation graph. Okay. Now what it does is nodes are the process. Okay. Instead the process and the resource. Okay. Now that vertex is now just simply a process. If P of I has a direction edge to P of J, means P of I is waiting for P of J. Okay, Pi is waiting for Pj. Okay, process I waiting for process J. Then you periodically involving this algorithm to search if any circle in the graph. If there's a circle, that means there existing a deadlock. Then you have an algorithm to detect a circle. Okay, in a graph, my request order of n square operation with n's number of vertices. Okay, n's number of process in the graph. Now, the resource allocation graph converting into waveform graph, the corresponding waveform graph is very simple. Okay, if by looking at this example before, we have what? P1 is requesting for R1, right? The R1 is the resource currently held by P2. So by this, simply changing to P1, okay, is waiting for P2, right? P1 is requesting for R1, right? R1 is held by P2. It simply converted P1's waiting for P2. Similarly, P2 is requesting for R3. R3 is holding by P5. So you simply convert P2 is waiting for P5. Okay, so on and so forth. So therefore, on the left side, you will have the resource allocation graph, which we learned before. On the right side is corresponding waveform graph for the left side of resource allocation graph. Okay, any question? So that conversion is quite simple, right? I simply convert from the resource allocation graph by, if I request some resource and that resource held by other process, then that process is waited for P certain process to finish. Okay, all right. So once I have that corresponding waveform graph, I need to check if there's a circle in the waveform graph. Okay, quite simple. If there's a circle in the waveform graph, then there's a deadlock. Okay, all right. So in the several instances, so that's a single instance is always easy. Okay, in the case if you have a several instance of the resource type, then you need to do a similar thing as the Banker's algorithm. You have available. Okay, available is a vector of length of m, indicating the number of available resource for each type. Then you have allocation vector, allocation matrix, which is n by m matrix, which is defined by the resource for each type currently allocated by other resource. So same thing. The request is the n by m matrix, which is indicating the current request for each process. If the request ij equals to k, then the process I requesting k and most instant k most instant type of j. Okay, so those things are very similar as before. Okay, so now the detection algorithm is this: if you let the work and finish to be the vector, okay, so vector of length of m, which respectively similar thing as before. If you let the work equals to available, okay, for I equals to 1 to n, which you have a what? N of the process, right? So if the allocation of I not equals to 0, then finish of I equals to 4. Okay, otherwise finish of I equals to 2 means I allocate everything else, I finished it. Okay, so in that case, you try to find an index, you try to find a I, okay, or index I or process I, such as that. Okay, finish of I equals to 4 means what? The process has not finished. Finish of I equals to 4. The request of I, okay, is less or equal to work. I'm going to request. That request is now currently less or equal to work, less than available. That in the system. So allow that process to finish. Okay. So in that case, if no such thing exists, okay, then I go to step 4. If I go to step 4, if finish of I not equals to 4 and finish I equals to 2, okay, the request of I is less than equal to work, means neither one of this is not equals to 2, then I go to step 4. In step 4, I check first thing is this: if finish of I equals to 4 for some, okay, I where I is less or equal to 1 and it's great n is it's greater or equal to 1 but less or equal to n. In that case, this thing is a deadlock. Okay, means there's something is not finished, but I cannot grant this request. Okay, so in that case, that process is in a deadlock. Okay, or if a finish of I equals to 4, okay, so that P of I is actually the deadlock the process. Okay, so you need to do something toward to it. If that's not the case, then work equals to work allocate, work equals to work plus allocation of I. Finish of I equals to 2 means I'm going to get rid of process I because I can allocate whatever the request for process I and go on to the next I plus 1. Okay, so means I'm going back to step 2 to try to find an index of I such as that, any of this matching. So if any of this students okay, I'm going to go on step 3, continue on, try to find a set of process. Okay, again, that order does not have to be I equals to 1 to n. Okay, it can be anything. The order can be rearranged. I can execute 2 first and back to 1, 3 first and back to 1, so on and so forth. So that is not the order process. That is just the index from I to n, but that's not the execution of order of that process. So all you have to do is find an index. Okay, that index does not have to be guaranteed the sequence, the order of 1 to n. Okay, I continue to do so. If I continue to do so and I finish, then I know that there will have no deadlock. So the detection algorithm is once a while they run this algorithm to see if I can finish. Okay, if all the equals to false. Okay, all right. Sorry, if all finish of I equals to 2. Sorry about that. Okay, all right. So let's give a quick example. Okay, if I have I have 5 process. Okay, that process P0 to P4, which have 3 resources, A, B, and C. A has 7 instance, B has 2 instance, C has 6 instance. Okay, at the sum snapshot, okay, I have this allocation matrix, request matrix, and available vector. Okay, now let's say assume I'm find a sequence, okay, of a P0, P2, P3, P1, P4, which results finish of I, all equals to 2, okay, of I, okay. So in that case, okay, then what? Then I have a 7 to 6, okay. So this is the sequence we find, okay. 0, 2, 3, 1, 4 can be finished, okay, for all. And in that case, sorry, what happened? So in that case, if that order, if a P2 making a request for additional instance of type C. Okay, if you by taking a look in this one, right, the system, what are the safety, the system of safety? Okay, if the P2 making that request, right, of additional instant, but currently right now that after I finish, okay, this instant, okay, the available equals to 0, then the P2 making that additional request of the resource instant of type 3, resource C with 1 instant, that you cannot make in that request because there's nothing available. Okay, now can you reclaim the resource held in by P0? But you could, because right now at the P2, we say P2, right? P2 is execute. Okay, so the order is this. Okay, order is P0, P2, P3, P1, P4. Okay, means P0 finish, P2 execute, P3, P4, P1, P4. Okay, so the example is this: if the P2 making the request, additional request at C3, although it's P0 finish, okay, and return the resource. So P0 finish and return the resource. They allocate P0 actually requests 1 instant for resource B, but that return of the B cannot satisfy because I'm going to make additional requests at C. Okay, in that case, it's significant resource to fulfill other requests, other process requests. So in that case, if I'm making that request, the deadlock might exist. Okay, if for P1, P2, P3, and P4, if that additional request been granted. Okay, all right. So, so the sampling detection algorithm is to detect if I can grant that resource or not at an additional type of additional instant of the resource or at a specific order. Okay, so you can see, so detection algorithm is let it execute. Then if I can grant additional requests. Okay, now how do I use in this detection algorithm, or when do I use in this detection algorithm? How often do I involve? Because when you run a detection algorithm, you're probably going to stop the entire system, right? Because you're going to take an instant of the system and pause everything and run the algorithm again, run that detection algorithm to see if the current state is in a deadlock. Okay, so that might cost you a lot, right? So how do you, when do you run and how often do you run depends on how often this deadlock will likely occur in the system and how many processes might need to roll back, okay? Because for each of those processes that's in the circle, okay, they need to roll back in one of them, okay? So the detection algorithm actually involved in arbitrary, means there might be a mini cycle in the resource. You detect one, you might not detect more. So you will not be able to tell how many deadlock, now how many deadlock they process, how many processes that cause that deadlock. Okay, so detection algorithm only detects it. How do you deal with is another issue. Okay, so therefore, how do you recover from a deadlock? Okay, the first thing is, of course, very simple. I just avoid all the deadlock process, right? So by aborting, we learned that before. Aborting means that I'm going to roll back on every single one of them. Okay, so that actually costs the system resource. Now I'm going to roll back every single thing I have been processing. Okay, or I can abort one process at a time until the deadlock circle is eliminated. I can redo one by one. Okay. However, if I want to reduce, if I want to roll back one by one, I'm going to abort the process one by one, then what are the order I should choose? Okay, which one I should start with? Okay, I can, of course, using priority of the process. The low priority, I kill them first. Okay, or you can use in how long this process has been computed, or how much longer it actually needed to complete. If it's been processed for a long time, or if it's going to be a little while that's been going to finish, maybe I don't want to kill that process, right? So you can select which process to kill. It's good for the system utilization. Or actually, I can take a look on the resource the process being used. If the resource the process being using are a lot, should I kill them? Maybe it's a good idea, right? Because holding a bunch of resource means in that case, I should I should kill that process and return all the resources being held by that process. Okay. And the third one is how many process. The resource need, how much resource needed that process to be complete. Okay. If that process only need 1 or 2 process resource in order to complete, maybe I should let this process finish. Okay, then it get to release all the resource that this process being held. Okay, and the third consideration is another consideration is how many processes needed to be terminated. Okay, if I terminate this one, there's a child process or sub-child process, so on and so forth process that I need to be terminated. Right? Because if it's a parallel processing, once it has a child and parent or the consideration, if I kill a parent process, sub-child process will kill. How many processes related to this process if I need to terminate this one? Okay. Another one is you can take a look on the priority. Not priority. The process is interactive or batching. Okay. Should I kill the interactive process? Should I kill the batching process? Okay. You kill the interactive process, you have affect the user's experience of this process, the system. But if you kill the process, that's a batching process, meaning that actually executed quite a set number of process. So it means all those batching process has to restart it over again. Okay, so that might cause a system utilization. Okay, so those are some of the issues that you need to deal with when you do a process termination. Okay, so once you select a victim with some minimum cost, that might be a priority, that might be a number of resources that have been holding some minimum cost, okay, by requirement, then you can select a victim, roll back to some safety state, some safe state, and restart the process from that state and continue on. Okay, so you have to do a rollback always. If select a victim, you kill them, means you actually abort this process. By aborting, you need to roll back on everything that's been modified. Okay, then from there on, this could be a issue which is a salvation. Means some process might always be being picked as a victim to kill them. Okay, which if you select the lowest priority to kill the process all the time, once you detect a deadlock or a circular wait. So in that case, the lowest priority always get picked as a victim. Okay, then the rollback will always be some of them. Okay, so means that process might always get selected. So means the starvation could always happen inside of the process. Okay, all right. So that it's for today's lecture. Okay, any questions? 有没有任何问题？Sorry. A safety algorithm 不是发现了没有 resource 就会让 process wait 吗？那 deadlock 会是什么造成的？ deadlock 会是造成说在这一段的 process 里面 ，OK， it select, it let this process going, but additional, it might require additional resource. In that case, that process will create a deadlock, 或者是新的 process comes in, because the situation is like this. Okay, if I have a process currently, I can schedule it as a P0 or PP4. 但是你可能会有 additional process that comes in, then that might create a deadlock. Okay, so the safety algorithm just for now, okay, but additional process might still come in. Okay, all right, and yeah, so that's a situation. You can never really determine. You can determine at the current state, you can prevent that deadlock happening, but that deadlock can still happening. But in this case, 在这个地方我们讲的是 deadlock detection. Remember 我们在一开始有讲到有几种方式我们去 detect 去 guarantee the deadlock 嘛，对不对？我找一下。OK， 在这个 deadlock handling 我们有几种方式。第一种方式，我们 never let the system enter the deadlock. Means if you run a safety algorithm, means that guarantee the system will never enter the deadlock. OK， 刚最后我们讲的东西，在这里我们讲 deadlock detection 的时候，我们是讲 you let the system enter the deadlock, 然后 recover. Means now I'm going to detect them, then recover them. 这两个句是不太一样的。 你讲的这个 safety algorithm 是在讲尤其是你在讲这个 bankers algorithm 嘛，我 assume 你的 safety algorithm 是在讲这个 bankers algorithm。那这个 banker algorithm 的时候是在 guarantee the system will never enter the deadlock， 在这个 instance 里面 ，OK， 好，没问题。那还没任何问题？没有问题的话，我稍微讲一下因为有些学生可能礼拜五不会来做 listen 的 review， 我们应该是下个礼拜，或者是我可能在这个礼拜的时候找一个时间，我会 create 一个线上的模拟考试。哎，这个线上的模拟考试呢，只是让你去熟悉一下，哎，去让你熟悉一下，如果我用 Moodle 做线上考试的流程是什么 ？OK， 好不好？So therefore，下个礼拜我可能会 create 一个线上模拟考试，可能那个问题就是非常简单，从那个 home assignment 来的，所以你试着练习一下线上模拟考试的流程。我会放在 Moodle 上，我会用 Moodle 的那个 module 做线上模拟考 ，OK？ 那线上考试一样，还是在这个 assign 的这一天的这个时候，就是我记得是，如果没记错的话，应该是。想看哈，是在下个礼拜一 as a final exam， 5月30号是我们这一堂课的 final exam，OK， 所以在这个 final exam 的时候，我会要你到时候我会跟你讲说这些东西 ，OK， 到你应该怎么去就是执行 ，OK， 好不好 ？OK， 所以要稍微下个礼拜稍微注意一下Moodle 上的公告。我会做一次线上模拟考 ，OK，All right，OK， 好，那有没有任何问题？别的问题？
我有点分不出来那个 banker algorithm 跟另外一个叫 detection 的 algorithm。这样
detection algorithm 其实非常简单 ，OK，banker algorithm 应该懂嘛，对不对 ？banker algorithm 就是要试着做所有的，
就是我分不出来有什么差别。
它差别其实不大 ，OK， 它的差别其实一个是，OK， 好，我懂你的，它的这个 concept 其实是非常一样的 ，OK， 但是 bankers algorithm 的，因为一个是先不让它进入 unsafe state 嘛，对不对？那就表示 bankers algorithm 它试着 pretend 我 allocate 这个 request， 但是我不真正做 allocation。如果我的 allocation 完之后，我还是在这个 safety， 我还是在这个 safety algorithm 范围里面的话，我这个 allocation 就成立。如果我的 allocation 就成立的话，我就 allocate P of I。如果是 unsafe 的话，我就会把这个 P of I 让它下一次再执行，也不是说下一次，就是之后再执行，看看我能不能再执行 P。所以这个 safety algorithm， 它这个 bankers algorithm 试着要这样子 run 完之后，它会找出一个 set of order。OK， 那这个 set of order 会是 in这个 safety state 里面，但是这一个 algorithm，OK， 这一个 algorithm 它只是 detect， 我现在 detect 你是不是在 safety 里面。我不做 pretend 做这件事情，我直接 detect。如果你不在 safety algorithm 里面的话，你不在这个 safety state 里面，我就会 return false。那这就表示这个 system 是 in deadlock。它只是 detect 它而已，但是它的 concept 是一样的。
懂了。
OK， 好。OK， 好，还有没有任何问题？好，那如果没有问题的话，我们一样玩一次，应该最后几次玩我们的夺门而出游戏哈。你们等我一下。So I'm going to do a countdown, okay? So you can sign off. Sign off. Okay, you have a 10 seconds to sign off, okay? Let's start in front. All right. 好，记得一样哈，我们礼拜五还是有review 的时候，你可以看一看你的 slide，然后有问题的话可以提出来问，好不好 ？OK， 那yeah，otherwise you got free to go。如果你没有任何问题的话，you're free to sign off。你只要再签一次到，你就可以下线了。OK， 好，last one，哎，如果你还没有签到的话，I'm gonna cut off here。OK，all right，没问题，不客气。OK，大家都签到了哈。